Happy summer, everyone, and welcome to Beyond the Atoms. If you learned in middle school that the universe was made of protons, neutrons, and electrons, the fundamental building blocks of nature, you learned wrong. Now buckle up. We are going to do the real version, the standard model as of 2020. Print out or save your notes on the standard model, the particle zoo, follow along with the lecture, and decorate your notes as the new words come up. We are going to go through everything that's under the hood, beyond the atom, the standard model of particle physics. We're going to look at the proton and neutron family, also known as hadrons, and the electron family, also known as leptons. We're going to look at the force carriers that explain why the fundamental forces of nature do what they do. Let's get started. So here we are in the building blocks of matter. Everything you can see, feel, smell, and touch, this is what it's made of. We had said that we thought the nucleus was composed of protons and neutrons and electrons. Well, 1 out of 3 ain't bad. The electrons going around the nucleus are fundamental particles. They have a charge of -1. -1 what? -1 proton, and a mass of 0.5 gigaelectron-volts per c squared. I think I'm not going to get any questions on why we don't measure electrons by the kilo. Remember Avogadro's number? That was a teeny tiny pile of powder on the balance in chemistry class. And that was just atom by atom. That wasn't counting the number of electrons in each molecule. 1 electron volt is a unit of energy. Specifically, it's the energy needed to get 1 electron boosted across an electric field by 1 volt. Given that alkaline batteries are 1.5 volts, you can picture it as getting an electron 2/3 of the way to the top of the battery. Einstein tells us that E equals mc squared. More on that later. And that means if we want units of mass, we can do E, the energy, divided by c squared. Electrons are the smallest fundamental building blocks of matter that we know. They're stable. Turns out there's a whole family of electrons. In the previous lecture, we talked about the muon that was first observed in the 1930s and confirmed to be its own separate particle in the 1940s. Calling it a muon, the heavy electron, was a mistake. It was a mistake on par with several of the other mistakes of the 1930s that we're very grateful for, specifically the heavy water, H2O, made with deuterium instead of regular hydrogen, that took the Germans absolutely nowhere when they were trying to use it to build an atomic bomb. Thank God. Muons are heavy. They're 110 gigaelectron volts per c squared. So on 110 on a scale of what previously had been 0.5. They are very unstable. However, they're the most stable of the unstable particles. Specifically, if a muon is created in the top of our atmosphere. Why? Because some cosmic ray comes zinging down from the heavens and hits something. I'll bet you anything it was a nitrogen, maybe one of the electrons, maybe the nucleus, probably an electron's more likely. If it's not an electron in a nitrogen, probably oxygen is the next most plentiful element. It hit, they ricocheted off each other. There was some kind of particle interaction, some kind of decay. If a muon is created there at the top of the atmosphere, it will live for a matter of 2 microseconds or so before it undergoes radioactive decay and spits out something more stable. However, if you remember what we learned in the theory of special relativity, what looks like 2 microseconds to a muon would look very, very different in another inertial reference frame. For instance, our inertial reference frame here on the ground, where we're seeing those muons streaking toward us at a respectable fraction of the speed of light because they're so small. Yeah, 110 gigaelectron volts per c squared may look big. This is something slightly fatter than an electron. It can move pretty darn fast. How fast? Well, if you use the Lorentz transformations for time dilation, coming online to a physics expo near you, you will notice that what appears to be 2 microseconds in the reference frame of the muon. If you are Slim Pickens trying to ride that muon all the way down, we'll look closer to 300 some microseconds plus in our inertial reference frame down here on the ground, doing nothing, minding our own business. 300 plus microseconds is long enough for the muon to make it from the top of the atmosphere down to our detectors on the ground. This is why our QuarkNet team here at Rochelle Zell has a muon detector, and muons are just about the only particles we seriously study in our experiments. Yes, they're unstable, but their lifetime is long enough that when it's time dilated, they can make it from the top of the atmosphere down to the ground and be measured. In fact, most of the cosmic rays we track on Earth are muons, not because the muons came from space, but because other cosmic rays came from space and decayed in a shower in the atmosphere, and the muons were the products of that shower that lasted long enough to make it down from the ground. By the 1950s, it started to be clear that everything seemed to be coming in families of 3. And when Fermilab revved up the Tevatron in the 1970s, they were able to make the third member of the family, the tau. Again, there's the same negative charge. Why didn't we see a tau in nature? Because it is 1,800 units on a scale of 0.5. It is ridiculously unstable. If a tau ever is made in a subatomic particle interaction, and yes, they are, it doesn't hang around long enough for anyone to notice that it's there before it decays into something more stable. So, run your finger across your standard model. We've just completed the set of leptons. Now, as we talked about in November, it was obvious, even from the early days of the 20th century, that every time an electron or one of its relatives, a muon or a tau, is created, a chunk of energy goes missing from the experiment. Each missing chunk of energy is directly proportional to the size of the lepton. When an electron is created, a small chunk goes missing. When a muon is created, a medium chunk goes missing. And when a tau is created, a larger chunk goes missing. We talked about this in November, and we talked about it in terms of conservation of momentum. It wasn't just the energies that didn't add up, it was the momenta. And you can always say that there's another kind of energy out there in the universe that you just didn't know to take into account. Dark energy, the forefront of the 21st century. But there's only one kind of momentum. It goes oomph, and if it's not there, you better look harder until you find it. When we talked about conservation of momentum with neutron decay, whereby one neutron created one proton, and yes, one electron, we named this invisible, massless, chargeless particle the neutrino. Neutra for neutral, and ino because it's so small you can't see it. There are 3 flavors of neutrinos. We call them electron neutrinos, muon neutrinos, and tau neutrinos because of what they're created along with. Neutrinos do not show up in any of our conventional detectors. They have a charge of 0. They don't interact with positive or negative charges. They're not magnetic at all. When I started teaching, I also taught that neutrinos had no mass. However, in 2006, Super Kamiokande in Japan reported experimental confirmation of neutrino oscillation. That is to say, one neutrino can change flavors. It may be created as a tau neutrino, but it has the potential to turn into an electron neutrino and a muon neutrino after that, if the conditions are right. This is why I'm not teaching neutrino oscillation math in this first-year high school physics course, but the important thing is this. In the equation for neutrino oscillation, mass is found in the denominator. I'm going to say that again. Mass is found in the denominator. That means that the mass of the neutrino cannot be 0. You can't divide by 0 and get a real number. Since neutrinos really do oscillate, it means the mass cannot be 0. Now, we've never seen a neutrino in a regular detector. You need to build a special neutrino detector. These are the kind we have at Fermilab in Minerva and in Minos. They are so unbelievably unreactive, those neutrinos. The detector needs to be at minimum the size of a very large building, and better still, Dune, which is what Fermilab is working on now in 2020, is setting up the neutrino beam here in Batavia, Illinois, and the target is in an abandoned mine underground in Sudan, Minnesota, more than 500 miles, more than 800 kilometers away. This is the kind of scale we need to get a neutrino to interact with anything to let us know it's there, much less measure its mass. Super K in Japan, when they published their results, were not working in an experiment 800 kilometers long. They managed to confirm the upper bound based on the precision of their measurements. They know that the mass of a neutrino is less than the greatest accuracy they could achieve, namely it's less than 16 electron volts per c squared. Now remember, the mass of the electron was 0.5 gigs. That's 500 million electron volts, on which the neutrino clocks in at less than 16. So we're talking minimum 8 powers of 10 smaller than the smallest known particle. That's how small a neutrino is, and that's why we call it a neutrino and not a, well, neutra. Now, you see why there are two lines of leptons: the electron and its invisible cousin sidekick, the electron neutrino, the muon and its invisible sidekick, the muon neutrino, the tau and its invisible and equally unstable sidekick, the tau neutrino. The name for protons and neutrons is the hadron family. Protons, which we thought were so fundamental, have a charge of +1, and they're stable. Neutrons, which we also thought were fundamental, have 0 net electrical charge, and they're semi-stable. Neutrons are only stable when they're in a nucleus with enough protons to babysit them. You know that in chemistry, the difference between a stable isotope and an unstable isotope is the number of neutrons in that nucleus. There's such a thing as too few neutrons, but most often the radioactive isotopes are the ones with too many neutrons. See carbon 12, nicely matched up 6 and 6, and carbon 14, which has 2 extra neutrons, 8 instead of 6, and is unpleasantly radioactive, but can be used for carbon dating biological specimens. Now, let's see why protons are stable and neutrons, which are only slightly larger. Check out the conservation of mass in the radioactive decay. The mass of one neutron is equal to the mass of one proton plus the mass of one electron. A neutron decays into a proton and an electron plus an anti-electron neutrino. We'll get there in a minute. We know whenever we make an electron, there's a neutrino there too. And the neutrino's mass is so small, it doesn't feature into the first 9 or 10 significant figures. Now, let's see why the heavier ones are less stable. Before we get into the question of neutron decay, I want to check in with another subatomic particle and the question that brought us in from the 1950s and into the 1960s. And it's pretty amazing that we got to the 50s and 60s before getting this fully answered. Again, in middle school, you were taught the Bohr model of the atom with the electrons running around in pairs on the outside, and we debunked that pretty thoroughly in the previous lecture, saying electrons are like charges. They don't travel in pairs. The Pauli exclusion principle has to do with quantum numbers, not electrons traveling in pairs. But we didn't make the logical extension of that argument into the nucleus. What's wrong with this picture? All the protons and neutrons fused together in a big lump in the middle, electrons on the outside. Pause this video and see if you can figure out what is wrong with the basic chemistry model of nucleus. Why ought it not to be allowed? Well, as we worked out in class on your observables and unobservables worksheet, protons are like charges. They repel each other. They don't stick together any more than the electrons stick together. Now, those of you who are going to say, well, maybe the neutrons, which have no electric charge, are in the nucleus and they're babysitting and they're gluing the protons together. Wait a minute. More neutrons means it's less stable, not more stable. Pause again. Text some friends. See if you can come up with some kind of hypothesis. What on earth can be gluing this crazy nucleus together that is stronger than the Coulomb forces, KQQ over the world's smallest r squared, no more than the diameter of an atom, and keeping that nucleus from blowing itself to bits as positive charges repel each other all the time and take off like little billiard balls. See what you can figure out. Remember, more neutrons means less stable. Ready to figure out what works? All right, let's go. There has to be another force. There's no other solution. The force of electrostatic repulsion can't be the only force here. There must be another force that is stronger than all the Coulomb forces in the world put together. So strong that it's able to glue a whole ball of positive charges together. There must be another particle in there, another particle we can't see. There must be some kind of glue that enables that other force to exist. We know that forces come with force carriers. We saw this with electricity and magnetism. We know that when the two electrons repel each other, it's because they're undergoing a virtual photon exchange. And if two protons in the nucleus were repelling each other, they must be undergoing virtual photon exchange too. They're like charges, just like the electrons. That means that in addition to those photons getting traded, there must be other particles acting as a glue so that when the protons trade those photons, they don't ricochet off each other due to conservation of momentum. Conservation of momentum works in a closed system with no outside force interfering. This cannot be a closed system. We may have forgotten something on the list, and there must be another force. All right, so let's talk about the strong nuclear force. How strong is the strong nuclear force? Well, it's strong enough to overcome the Coulomb repulsion between two protons, which, as you calculated on your worksheet, should be strong enough that after more than 1 second, both protons should be ricocheting away from each other at considerably more than the speed of light. Protons are not fundamental particles. If they were, they wouldn't be sticking together in the nucleus. Protons, neutrons, and their relatives are made up of quarks. And from the patterns of what we do see and what we don't see, as you saw on your unobservables activities, we've noticed that they seem to come in triples and in doubles. Quarks are glued together by the strong nuclear force. The particle that we describe as mediating the strong nuclear force is the gluon, drawn here Feynman style with these little squiggly springs. Gluons, as our model goes, are incredibly, incredibly valuable. They're so valuable, if you're a gluon collector, that there's no possible way in the world, if you got a hold of a gluon, that you would let go. You can picture each quark as having two hands and holding on as tight as it can to one gluon in each hand. Now comes the neighboring quark and holds on to the other end. Neither one of them is willing to give up a hold on this incredibly, incredibly valuable gluon. So they stuck together, each holding on to one end of the gluon. These three quarks glued together make up protons and neutrons. And because these hadrons, as we're going to call them, these quarks, have such a strong affinity for gluons, That is to say, according to the model, they're sticky. The same gluons can glue two protons together in the nucleus. That's why they call them gluons, because they're the glue that holds the nucleus together. I know, we're particle physicists. We're really bad at naming things. So let's take a look at the building blocks of the hadron family. Hadrons, again, being things that collect gluons. First on your chart of the Standard Model is the up quark. The up quark has a charge of positive 2/3. 2/3 of what? 2/3 of a proton. A mass of 2 mega electron volts per c squared. So we're talking on the scale of 1/100th of an electron, because this is only 1/3 of a proton, and being so small, they are very stable. However, the down quark, its partner, the negative quark with a charge of -1/3, has a mass of 5 mega electron volts per c squared, and it's semi-stable. It's more than twice as heavy as the up, which is why it's less than twice as stable. Let's do the math. Pause, do the algebra in your head. You want to make a proton charge +1. How would you combine 3 quarks? Remember, we've noticed these hadrons come in 2s and 3s to make a proton. Press play to check your work. All right, here we go. 2/3. 2/3. That's 4/3. -1/3 makes 1. A proton is 2 ups and a down, and that makes it stable. Now think about a neutron. This should be a little bit easier. You're in good practice. You want something with a charge of 0 made of up quarks and down quarks. Why are these fractional charges? They're fractions of a proton. We know that these quarks tend to come in 3s. Pause, figure it out, plus play to check your work. Ready? That wasn't too bad, was it? 2 downs and an up give you a neutron. That's why neutrons are less stable than protons. They're made of heavier down quarks, which were already semi-stable to begin with, and 2 of them are going to be nothing but trouble unless you're in the company of protons stuck together with gluons from the same set, where you've got plenty of stable particles to go around. Now at this point, we really thought we had everything. Protons, neutrons, what's not to like? What's not to like is 1947 and the discovery of the kaon in cosmic rays that was not made up of ups or downs. It had this weird factor called strangeness, and people were banging their heads against the wall for about 14 years trying to figure out who ordered that. Messing up our views of matter indeed. Unfortunately, there's more coming in from the sky in cosmic rays than there is in matter as we know it. And Murray Gell-Mann in the 1960s put forward quark theory, for which he won his Nobel Prize, and put down that the idea of strangeness, and don't even get me started on isospin, was the fact that there was a third quark, a strange quark. Originally, we thought strange quark went with up, but when we did the math and figured out that the only possible way that matter could be matter and cosmic rays could be cosmic rays is if it had a negative charge, then strange appeared to be a heavier version of the down. And since leptons come in 3 generations, small, medium, and large, it makes sense that these up and down quarks also might come in 3 generations of small, medium, and large, and that would have meant that there was another quark here in the up family that was eventually discovered in the 1970s when we could build machines with energy that much. There it was, next positive quark. And the reason we really had to hunt for it among those cosmic rays is that it has a mass of 1200 megaelectron volts per c squared, or 1.2 gigs. It is ridiculously unstable, given that it's only still 1/2 or 1/3 of a particle. Now, people who were looking in mesons and cosmic rays for quark pairs thought that charm had a pair. They called it charm because they were calling the pair charm and beauty. I told you, particle physicists, we just can't name things. Give us Nobel Prizes for discovering how the universe works, but just feel grateful that they'd call their children Bob and Andrew and not anything weird like this, charm turned out to be the pair for the strange. So they renamed the beauty quark, the B quark, B for bottom. Look how unstable that is. That's 4.2 gigs. And they started looking for the top quark. And the top quark is where I come in. I was a low-rung computer programming gopher processing the data from run 1 in preparation for round 2 of Fermilab, the 1994 run wherein the top quark was discovered. Bottoms and charms occur naturally in very rare types of mesons and cosmic rays, but top we had to make in the lab because it has a mass of 173 giga electron volts per c squared, the heaviest subatomic particle, I should say quantum, we know, and that's why it never sticks around for long enough in order to be recognized. So let's put things together what we've figured out about the strong nuclear force. The strong nuclear force is mediated by a little force carrier, or boson, that we call a gluon. The quarks fight over a gluon, and two quarks fighting over a gluon glues together nucleons and their other relatives, what we're going to call the hadron family.
My blue gluon.
Mine.
My green gluon.
Mine.
My red gluon. Mine!
Pattern is associated with triples, baryons, like protons and neutrons, and doubles, the mesons we find in cosmic rays.
My green gluon.
Mine! My anti-green gluon.
Mine.
Look, we've got sets of quarks. We can work through all the permutations for spin, for momentum. You'll see protons and neutrons. You'll see sigmas. You'll see chi's. And pair them up 3 by 3 and 2 by 2. You'll see the rest of the 36 cosmic rays that are out there. Notice that the main way we've been drawing these gluons and deciding which one is which is by color. Unfortunately, this is just a model, like flavor. Be grateful we called it color and we didn't call it chocolate, vanilla, and strawberry, okay? We're particle physicists. Names are not our forte. But it's how physicists organize a set of rules for which 3 is okay and 2 is okay, but no other combination. 3s we're going to call white. Every stable baryon is stable because it's got a complete set of gluons, one red, one green, and one blue. Now, fact, gluons can oscillate like neutrinos. They can change color under certain conditions. A red gluon isn't going to stay red forever. But at any given time, a stable hadron has 3 gluons gluing its quarks together, R, G, and B. A meson, 1s and 2s, we're going to code as black. We're going to say that this particle has a red gluon, this particle has an anti-red gluon. They cancel each other out and make black. And that's how we know we've got a stable meson. Blue and anti-blue, green and anti-green, or red, green, and blue, or anti-red, anti-green, and anti-blue. We're now into the 1970s, the big experimental period, the glory days of our own Fermilab here in Batavia. Let's finish up the last column of the Standard Model as we knew it then. There's a column called bosons. No, there isn't a boson's mate. Boson means force carrier. Notice that with the bosons, not all of them have mass. Calling them particles is a grave misnomer. They're quanta, and you'll notice this because the next one down the list is the photon. We studied photons when we talked about QED in the last lecture. The electromagnetic force is the reason that like charges repel and opposites attract. This force is mediated by how the charges trade or share photons. When moving electric charges go zap, you can see the photons as you see the sparks fly. Photons have no mass, not neutrinos. They don't oscillate. Absolutely no mass whatsoever. They have 0 electric charge, but we can see them, so we're definitely sure that they're there. Now, let's talk about the next force on our list. we've noticed a trend throughout the entire Standard Model that light particles are stable, and the heavier you get, the less stable you are. Why? The answer is the electroweak force, also known as the weak nuclear force. Why the weak nuclear force? The weak nuclear force, well, because it's not as strong as the strong nuclear force. I like to think of the weak nuclear force as yo mama's force. Why? Because yo mama, she's so fat, she gonna dump a vector boson any day now. That's the way it works. If you have an incredibly massive particle, you are more likely to make a vector boson. Fact. It's probability. E equals mc squared. If you have a lot of m, then you have a lot of mc squared. And that means you're going to have enough energy to be a complete spendthrift, to make whatever kind of crazy particles you want, to make some horrifically bad decisions. I like to think of the weak nuclear force as the Red's sports car of particle physics. How likely are you, I mean you personally, to run out and buy a red sports car? Not likely, huh? Why? Well, the answer I get from everybody in the class every year is, I don't have enough money. All right, let's add some money. Let's give you $100,000. How likely are you to buy a red sports car? Again, I look around the room, I see 0 hands going up. What are you going to use that money? Just about everybody says, I'm going to use it for my college tuition, though some people want to buy their parents a nicer home, or help out with grandma's medical treatments, or some other such noble goal. What about $1 million? Let's just keep upping the ante. How likely are you to get a red sports car? Yeah, okay, I see 1 or 2 hands going up, going me, and other people saying that they're going to pay off all their siblings' student loans, get their parents a nicer place to live, maybe give some tzedakah. I see, people talking about foundations and big projects, and yeah, a couple people buying cars. All right, you have $100 million. How likely are you to buy a fancy car? Oh, okay. All right. Now I'm starting to see some fist bumps. Now I'm starting to hear people talk about their favorite brands and the fact that they don't really care for the color red. Sooner or later, if you have that much money, you are going to blow something on something big, fancy, and stupid, with or without a homewrecker riding it. I'm seeing people in my generation and the generation before who are living happy, stable lives with happy, stable families, when all of a sudden the company nails a really profitable deal or a really powerful client, and then people start running around like they're Superman, like they're invincible, like they can do anything. And the rest of their families are like, what on earth is wrong with you? And I'm rich, tends to lead to some really bad decision making. Particles who use some of their E equals mc squared to buy vector bosons are not happy, stable particles. They are particles going joyriding in a red sports car with no speedometer, and that problem is going to end really soon. Honestly, it's simply a matter of probability. How likely is that subatomic particle to blow some of its E equals mc squared on one of these flashy red sports vector bosons, and how long will it last once it does? I can answer that next one. Not long. Particles collide in labs like the LHC, like CERN, like Fermilab. They collide in a detector. They make other particles in the collision. Those other particles spray in jets all over the place, and we look at them in calorimeters. A very heavy particle, sooner or later, will use some of that enormous energy to create a vector boson. Those bosons are the carriers for the property that we call radioactivity. They are ridiculously unstable. They are viciously radioactive. Once they've decayed into other particles, those particles also having lots of energy, will continue to decay until they are so small, E equals mc squared, that they don't really have enough energy to waste on things like vector bosons. What are the vector bosons specifically, you ask? Let's take a look. Here, that looks like a pretty good collision to start with. A cosmic ray from space came and hit something in our atmosphere, creating this shower of particles that we measure down here on the surface in our detector. Hello there, muons. Most of you are going to make to the surface. Hello there, almost everybody else. We will have to track you by your footprints. If we're down here, most of what we're going to be seeing are electrons and neutrons and protons, with the occasional muon to spice things up. We either need to put our detectors up here, or we're going to need some really good math to see these pions that started the process off. Unstable particles decay three ways. If the original was neutral, it's going to make a Z. We call it Z0 for neutral. If it's a charged particle, there's a W plus for positive charge and a W minus for negative charge. These two W's have identical mass and identical properties except for the electric charge. The Z is a creature all of its own. You can measure it has a very distinct mass. That was the project I was given as an undergraduate when I wanted to do particle physics. Here, kid, take a quarter of independent study. See this data, make a spreadsheet, make a histogram, find the mass of the Z. You get what we get, you're on the team. All of those, the Z's, the W plus, and the W minus, have tremendous E equals mc squared. You can see from your notes on the Standard Model, they're ridiculously massive. We're talking 5 figures, where the previous hadrons, the quarks, were 3, and that boson can decay into other hadrons or leptons, making whole sets of interesting chain reactions and jets. We've got electrons here, and positrons, and gamma rays that we know are photons, and over here we've got hadrons in the neutron and proton family, and muons, which are leptons. It can make anything. That's why radioactivity is so unstable and why it's seeded by something like uranium or plutonium, which is just too heavy for its own good. Now, what's this positron that we were talking about? Now, let's put this idea of conservation of mass and conservation of energy together with the idea of conservation of matter count. What is this positron, which I referenced, or beta radiation as you called it in chemistry last year? What does it mean, antimatter? First, let's check in with the means of production. E equals mc squared. If you have enough E in that particle collision, you can make mc squared. You can make heavier m, or you can leave the m the way it is, or less m if the vector bosons have anything to say about it, as you have a tremendously high kinetic energy, a low mass particle moving very, very energetically. But either way, you're going to have to pay the price. What's the price? Price is matter count. Here is our energy. Let's take our cookie cutter and make some matter. What's left behind in the great cookie dough of E equals mc squared, if you take the cookie cutter and take out some of the cookie dough to make a cookie, instead of formless energy from the void, you have a definite quantum of mass. You can see what's left behind. It's not pure energy, it's that hole where the energy used to be and now it isn't. We call that hole antimatter. Conservation of matter count is completely different than conservation of mass. Conservation of mass is simply a subset of conservation of energy. At the subatomic level, mass is not necessarily conserved. You can crash 2 particles together. General joke among particle physicists is you can crash 2 tennis balls together, and if they're moving fast enough, you can have a bowling ball flying out. However, matter has its own properties. It's integer. If you start with 1, 2, 3 pieces of matter, for instance, 3 quarks and a proton, you jolly well better end with 1, 2, 3 pieces of matter. For instance, if we're looking at neutron decay, where we first worked out that math, 1 neutron decays into 1 proton and 1 electron. Doesn't work that way, folks. Matter conservation is a basic law of the universe. If you start with 1 piece of matter, you're going to end with 1 piece of matter. If you start with 0 pieces of matter, a void, you had jolly well better end with 0 pieces of matter. How does this work? Well, if you just made 1 mass plus 1, you've also made 1 piece of antimatter with antimass, a mass of -1. -1, +1, matter count of 0. Matter is conserved. And that's how we get the rest of the properties. Antimatter has opposite charge. It has opposite spin. It has opposite quark color. Those were the anti-reds, the anti-blues, and the anti-greens we were talking about a few minutes ago. It also has negative matter count. Does antimatter have anti-gravity? Well, we'd like to say that it is, but we can't demonstrate that experimentally, and this is why. Which force is stronger? Electrostatic repulsion or gravity? Check it out. An electron, which is made of matter, has a negative charge. A positron, which is made of antimatter, has a negative charge. How are those charges going to feel about each other? That's right, they're going to attract. Now, look at Coulomb's constant, look at Newton's constant of universal gravitation as found by Cavendish. This one is 8.99 times 10 to the 9th. This one is 6.67 times 10 to the -11th. If the two masses have anti-gravity and they're repelling each other, positive and negative mass, just like positive and positive mass attracts, that force is going to be beaten into the ground by about 20 powers of 10 of attraction. We're never going to see anti-gravity with matter and antimatter because the electrical forces are going to get in the way. However, if you continue doing the math, you'll see that once the electron and the positron are attracted to each other and they actually collide, you're going to have negative charge, positive charge, 0, upward spin, downward spin, 0. Electrons and positrons don't have quark color. They're not hadrons. They don't collect the gluons. Positive matter, negative matter, 0. The two of them combine together to make pure energy, the pure energy that we started with when we put the cookie that we never really meant to make into that shape back into the cookie dough, fill in the hole, and there's no more mass, just energy. The energy we started when we made the pair. With that information, I'm able to tell you why it is we're so sure the gluons are there without anyone having experimentally verifying this by catching a free gluon in the lab. We've made tau neutrinos. We've made top quarks. We've found Higgs boson, but nobody has ever seen a singular gluon. And this is why. If you try to pull 2 quarks apart to see the gluon inside, you won't be able to do it. Why? Because gluons are so valuable to those quarks. The energy you need is so immense that by the time you've revved up your tevatron or your Large Hadron Collider to a high enough energy where you could, in theory, pull those quarks apart, you will find that although you thought you were operating in a vacuum, all of a sudden, pop, 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 pop. You're not operating in a vacuum anymore. There are 2 or 4 or 6 little pairs of matter and antimatter orbiting each other at ridiculously high speeds because that's where your energy went. It's a probability game at this stage. By the time you've inputted enough energy that you could pull two quarks apart and get a free gluon, it is more likely that you will create matter and antimatter out of thin air than that you will succeed in getting those two quarks. My red gluon.
Mine!
My anti-red gluon.
Mine!
Ah, see that? You're likelier to have that happen and create that matter and that antimatter than you are to convince those two quarks to let go of their gluon. It's happened every single time. We've given up. What about the matter and antimatter? What happens to them? Well, if they're not moving very fast, then that electrostatic attraction could take over, and there won't be matter or antimatter around after that. However, if they're moving very, very, very fast, like the Earth and the Moon, they could be moving too fast to hit each other, in which case positive charge will spiral one way in the magnetic field, negative charge will spiral the other way, and both of them will be detected by our detector. In the 1990s, the Standard Model was square, 4 by 4 by 4, with 4 force carriers all lined up. One little tiny problem. We still didn't have a force carrier for gravity. Well, we still don't. We have theorized that gravity is propagated by the graviton, since every other force seems to have a force carrier, the photon for the electromagnetic force, the gluon for the strong nuclear force, and 3 different kinds of boson for the weak nuclear force. We haven't observed gravitons yet, although we did turn out to be right about gravity propagating through the universe in waves as a perfectly viable alternative to news traveling instantaneously from one planet to another, thereby breaking Einstein's postulate that nothing can travel from here to here faster than 3.0 times 10 to the 8th meters per second, formerly known as the speed of light, not even news. What we do have, as far as gravity is concerned, is the Higgs boson. The Higgs boson was discovered in 2012 when we turned on the Large Hadron Collider in Switzerland, and the Higgs boson is the reason we have mass. The Higgs field propagates throughout the universe like an electric field or a gravitational field. However, the electric and gravitational field are radially symmetric around the vacuum. That is to say, the graph looks like a graph of a parabola. If you were to put a particle on this energy graph, AP physics style, and let it oscillate back and forth until it eventually worked off all its energy to some sort of outside force and settled, where would it settle? Well, it would settle right here at 0. What's the electric field in a vacuum with no charges around? Well, it's 0. Similarly, what's the gravitational field infinitely far away from any stars or planets or galaxies? Again, it's 0. But the Higgs field does not have a local minimum at 0. It has a local maximum. The Higgs field, if you leave something here to just work off through outside forces and run out of energy, sooner or later, it's not going to come to rest at 0. 0 is a point of unstable equilibrium, as we said when we did center of mass. The point of stable equilibrium for the Higgs field is over here. And that means the state of the Higgs field in a vacuum, infinitely far away from everything, is not 0. There are Higgs bosons there. There are Higgs bosons in a vacuum. Well, I thought a vacuum meant it didn't have any mass. No, a vacuum meant it didn't have any matter. Higgs fields aren't matter. They're bosons. The original description of how the Higgs field permeates the universe and given its mass was the analogy of rain and raindrops, that the Higgs field permeates the universe like a perpetual shower of rain. Some materials in the shower of rain, like leaves, just get wet. The fact that they're out in the rain doesn't fundamentally change their properties, like size or color or mass. But for some porous materials, like sponges, they have an affinity for water. They absorb water. Being out in the rain does change their properties. It changes their mass, it changes their size, it changes their shape. So, things like electrons and protons and neutrons have an affinity for Higgs, just like they collect photons for having electric charge, and the protons and neutrons collect gluons for having the strong nuclear force, being nucleons. They are glued in the nucleus. Then there are materials like photons and gluons that have no affinity for the Higgs. They get wet, but unlike, say, a water balloon, they don't change their properties depending on how much mass they can hold and how much E equals mc squared they can deliver when you bump into them. More recently, Higgs bosons have been explained using the paparazzi model. Quanta that do not have mass are invisible to the paparazzi. People go about their daily business. Nobody actually notices or stops or forms a crowd just because one particular person is buying sandwiches. Oh, but wait a minute. Wait a minute. This one is a celebrity. This one does have mass. This one has a very high mass. How high? Well, this one is so massive that it needs a police escort just to get through the Higgs field. So as far as the Higgs field is concerned, here is a photon or a gluon with no mass, or a neutrino with very little mass, and here is a much more massive particle. This is going to be something more like a charm quark, or even a proton. So the end result is that certain particles have no inertia, they move through the crowd effortlessly, or little inertia, hardly anybody knows who cares who they are, or very, very high inertia, that is, they collect a lot of Higgs bosons and have to fight their way through the universe under police escort. They are hard to start moving, and once they start, they're hard to stop moving. So there you have it, folks. The invisible, sometimes massless, sometimes chargeless dreams stuff is made of. We've got 3 generations of matter: small, medium, and large, stable, moderately unstable, ridiculously unstable. We've got a force carrier to explain how each force propagates through the vacuum across the cosmos: the strong nuclear force, electricity and magnetism, radioactive decay as we know it, and mass as we know it. Stay tuned over the next few decades for the discovery of a graviton and further developments in the standard model of particle physics.